Okay. Okay, good morning, everybody, and welcome to the OCP HPCM Thermal workstream discussion. So I wanted to today, as those of you who've been regularly attending, see if we can make some progress in the various sections of the DOE Oak Ridge National Labs New Frontiers proposal. So I put in the email I sent out last night, I put 3 basic topics that I wanted to maybe try and cover. So I guess the first thing to mention was on the last meeting, I think Michael was there, we had Chris Chapman from Boyd on, and we had a lengthy discussion around the fact that Boyd felt we would need to have a much more sort of stronger structure that could withstand 40 psi and have like a dual cooling mechanism, one for the main chip and another for maybe the rest of the components on the top side of the board, like the power supplies. So that was that would be a detraction from where we're at. And I think Chris also mentioned that in order to get the pressure, we'd need far more screws and we need to be closer to the actual chip itself. Otherwise, it would blow apart the way we've got it designed at the moment. So now, all that being said, I think Boyd are also looking, their eyes are heavily focused on cooling 3.5 kilowatts of power in one of these chips. And we want to get up to 1 kilowatt. I think it would be nice to go higher. And the design we have at the moment is this fairly novel little mini immersion chamber with using University of Illinois research that they done that we could conformally coat the boards to insulate them and then add copper. And Peter Salmon's just joined us as well recently, and he presented to me some of his ideas, and it looks like he's thinking along the same lines in terms of the conformal coating approach to the cooling. So I put the two together. I put Peter and Nanand at the University of Illinois to get chatting, and I've chatted with both of them as well. And long story short, I think there may be some legs in this immersion, in this conformal coating approach being more efficient. And also, over the years, Peter brought up actually bringing to boiling point, making this a 2-phase solution. And back at OCP Prague, I was talking to John Summers from the RISE Institute in Sweden, and a few of his colleagues, and listening to their Q&A at the various Thermal Prague discussions, and he brought up the topic of boiling of water and I guess pulling a vacuum to boil water, and Peter has highlighted that would be also very effective. So, I mean, I guess where, just in me thinking about it, Boyd's solution is probably, the tried and trusted way, and this is a novel way. And I think that, well, I guess Peter and Nanad have given me a little bit of hope that actually we might be able to, this actually might be an interesting new solution that is actually very effective at cooling quite serious wattages. So, and the other thing that Chris said at Boyd was, I think they've got a lot of their own IP and they're a little bit scared of sharing it. And he's happy to contribute to OCP, or they have in the past, in terms of helping to analyze and prove, some of the ideas in OCP, helping to really just to assess new ideas that are already sort of openly being discussed. So they potentially could still help us out as well. So I guess just where we're at in terms of being practical, one, I think it could be interesting to the DOE. It's a different way of doing this, worth exploring. So therefore, it is a thread to pull, and to run to ground as to whether this could be an effective method for cooling and how you get it to work. So I think that makes it quite an attractive part of our proposal. It also makes it extremely simple, and I get the impression that even Chris from Boyd and his people will say, you know, if we're cooling devices that are 500 watts or less, it will probably be fine as well. And so I'm sort of trying to get into this, you know, if we get co-packaged optics working, then maybe we don't need quite as much thermal density going forward, etc. I don't know, but I mean the trends will dictate what happens. But so anyway, so I mean, long story short, I really felt that maybe to really keep it practical in the proposal in terms of what we're asking of the DOE in this thermal management section is we should be looking at just one, this use case, this immersion use case, maybe with the potential of introducing two-phase, in fact, just analyze both of them and see how effective that is at being able to cool a kilowatt up to a kilowatt chip.
Can I make a comment, Alan?
Yeah.
So I ran the numbers, and if you calculate the cooling effect of heating water from 0 to 100 degrees, and you call that X, and then you boil the water and you call that Y, then Y is actually 7 times greater than X.
Say that again.
So comparing the single phase with the two phase.
Oh, right.
If you take the water and you heat it from 0 to 100, and you calculate the amount of cooling and call it X, and then you boil it and you call that the amount of cooling Y, then Y is 7 times greater than X.
Wow. Yeah. So the two phase, I think that was what you said to me in that other meeting. So then it begged the question of, can we pull a vacuum effectively? Could we design a loop to pull that vacuum? I think you were saying we might need some AI to sort of train it and learn how to do this, or so you get the boiling point nicely on each of the devices.
Yeah, so I looked at it, and if you get to 0.4 of an atmosphere, the boiling point is like 65 C.
Right.
But that's a significant stress on the system.
0.4, right? Okay. So yeah, that's so. I mean, in that sense, would a PCB collapse, or how thick would a lid made of aluminum need to be, or would it need to be made of something else, etc.?
Well, you know, so you can rib the lid, and you can do things, but I haven't done that analysis.
Right, right. So I have no idea when it comes to, so 0.4 of an atmosphere, I guess we're sitting in 1 atmosphere right now, I presume. So 0.4 is a substantial drop. But I guess the only other thing I've got is the submarines going down into the ocean, like the one that just collapsed and killed all those guys for that crazy dude. What atmospheres are you at down? That's not really a vacuum. That's just like external pressure, though, isn't it? So that's different, I guess.
But the mechanical design problem is similar, and I think it's hundreds of atmospheres.
Okay. So we're not we're not talking collapsing. Okay.
Now, well, you still have a similar problem that we talked about last week with that bottom cover. That I think you were talking 20 or 25 pounds of fluid pressure on the inside, and there was concern that you would bend the cover and it would cause leaking. If you're at 0.6 atmospheres, you're at like 8 psi or so on the outside instead of the inside.
Oh, is that right? Okay.
Because it's about 14.7 or something like that PSI at sea level. So if you're 60% of that, then that's what the pressure would be on the surface of the outside of that bottom cooling plate. So significantly less than what it would have been with the pressurized water on the inside.
Well, that sounds fantastic, Michael. I don't know, in my basic so, and not only that, I was thinking the other thing here is we're actually sucking rather than pushing from the inside. So therefore things are being pushed together, whereas in the other, they're being forced apart. So pulling them together would make them seal better. It was my sort of mental picture, whereas the pushing apart causes all the leaks for the air to get, for the water to get out. Anyway, is that what's that? And again, look, by the way, I am completely out of my domain here, so I could be. Tell me if I'm talking complete rubbish, because that's fine. I probably am.
Well, Peter was talking about putting ribbing and stuff on that bottom cover, and you'd have either with inside pressure or outside pressure because of the vacuum, you'd still have to do something to reinforce that plate.
Okay. Well, and then obviously we've got the PCB that we've conformally coated itself. It's going to be a 2 mm thick laminated PCB, right? So, and it's going to have sort of vias in it that are probably only micro vias. I would recommend that we would be an HDI stack up, so there would be no through hole ones that you could. But it's like, would that withstand 0.4 atmosphere? So I guess, you know, it'd be nice for us to go into this proposal and explain all this and actually sort of have some wet finger stuff saying, look, we think this sort of makes sense, rather than it's obvious it's never going to work and we got to start from scratch. I think that would be where I've been. So if somebody with a semblance of knowledge of this looks at it, says, well, okay, yeah, I mean, it pencils basically, but the proof of the pudding is in the eating. So that's what this stuff's all about.
Does the printed circuit board, is it just a raw PCB, or could you actually laminate it to a piece of metal to reinforce it?
Well, so first of all, it is going to be, in terms of its assembly, don't forget we've got the manifold on the back.
Right.
Well, let me just bring the model up. So this piece is the wall. So let me just get rid of the wall. So effectively, there's a PCB in the middle there, right? And this here is the little immersion chamber. This is the
that's the mechanical problem right there, because if you take the surface area of that part and multiply it by surface area in inches by the pressure in inches. So if you were going to run 25 or 28 PSI times how many square inches that is, you have a lot of force on that surface there. And that's
you mean like the center is going to bear the biggest, so it's going to be sucked in, you mean?
Or pushed out, depending on which cooling system. That's what the gentleman from Boyd was talking about last week.
Right. No, completely agree. He was saying you need more screws here, and you need them closer to the chip, because he had this two-phase mechanism where he had a separate loop for the chip, right? So that would mean more holes. That's
and he's trying to stop that cover from bending.
Right. But the pressure is 8 psi, you said, compared to he was saying 40 psi, right?
Well, whatever you'd use for the vacuum pressure.
Yeah. So, so obviously this lid at the moment, this is I've only got it as 1 mm thick, but there's nothing stopping us making this thicker, making it out of different material. We haven't necessarily even selected a material here. So, or putting some features in it. You said ribbing, was that what you said, Peter?
Right, yes.
Okay, so I mean, the design of this lid could be done to accommodate. I'm not too worried about this lid. I'm happy to make it thicker if we need to make it thicker.
Now the bronze colored stuff there is metal, I assume.
So this here is the actual manifold for the conductively cooling of these pluggable modules.
Aluminum.
Well, actually, I mean, this would be an expensive copper plate, but it could be copper, it could be aluminum. Again, we need to do the thermal analysis on this to see whether we can effectively cool what we need to cool.
And that's sitting right on top of the printed circuit board.
That's right. So if I peel this off, so this one here is there's a gasket between the lid and this stiffening frame around the PCB. And I was assuming that this would be glued, epoxied, or some way to give you a seal to the PCB. So that was, again, forgive my crude thinking. This is just the way I was thinking about it, without any real engineering understanding as to the ramifications. So this seal is on the PCB. This PCB is about 2 millimeters thick. I've got it at 2 at the moment. Again, that could be.
So the mechanical strength isn't going to come from the PCB. It's going to come from the copper that's up above it.
Right. Okay. Yes. All right. So in that sense, so if we just look at the copper up above it, let me just hide the PCB. You can see that we've got
lots of mechanical strength and lots of ribbing.
Right. Now some of these here, in reality, you can see, look, this is a little bit above. There is a gap between the PCB and here because there will be some components on the PCB. So it's not all going to be pressing up against the board. But the blue outline that you see here is what will be touching the PCB directly.
It would be a lot better if all of those ribs on there were pushing on the PCB, or as many as possible.
We could probably put some additional landing points where we do keep outs for other components on the PCB, would be the way to do that. So that's the other area. So we could raise multiple points where there are no components on the back of the board. So we could make it a little bit better than this, for sure.
Yeah. Otherwise, the vacuum's gonna, if you have a vacuum in that chamber underneath the PCB, you'll be pulling the PCB away from the copper, or pressure in it, you'll be pushing it toward the copper.
Yeah, so actually on the basis, we're discussing, just for clarity, I mean, we're discussing Peter's idea in terms of pulling a vacuum, right? So we'll be sucking the PCB down. So will this manifold have as much a need if you're actually sucking the board down? Then it'll come down to the bolting points again.
Yeah. So if I understand the mechanics of this correctly, the top side of the PCB that's in between your connectors and things there would have 14.7 PSI on it from atmospheric pressure. And you'd have some percentage of that below the PCB. So the atmospheric pressure would be pushing the PCB down in the perspective now, that be pushing the PCB towards us, and the bottom cover would be getting pushed toward the PCB. Yes.
Yeah, this cover would be being sucked towards the PCB, and the PCB would be being pushed towards the cover, or pulled toward. Yeah, right. by the outside pressure. Both the outside pressure on both sides are 1 atmosphere pushing in. Yes.
So if you're depending on the contact surface between the PCB and the copper piece there, the pulling a vacuum underneath it is going to do exactly what you don't want to see. You know, it's going to be
so actually, to be clear, this manifold is not really, its primary objective is not to cool this board. Is to cool these plugged-in modules and plugged-in cables.
But you said you had components on the other side of the board.
Yeah, so they might be gap padded to the I'm assuming the gap pad. You know, if you pulled a vacuum and you did pull it a fraction of a millimeter down, then the gap pad would continue to fill the gap.
Yeah, I just think you need to be conscious of the fact that the atmospheric pressure is going to be trying to push the board away from the copper piece.
Yes.
And then
then you're going to be reliant on the screws that are in there that are bolting the copper piece through the PCB, etc.
Yep.
So like the middle screw and the corner screws go all the way through to this to this copper piece. Whereas these are only going through to the to this stiffening plate.
Yep. So you've already got effectively ribs on the copper piece. Yeah, so the copper would be fine. The only thing is it's going to be captured around the rim. So the only screws that you have that are capturing the printed circuit board or around the outside
Yeah,
edge of
yeah,
the
yeah.
PCB.
That's exactly correct. Yeah.
So it would be interesting to do some finite element analysis on the PCB and see just how much that's going to bend.
So I guess that's sort of where this study would take us, right? I mean, it's a case of we need people's time, we need machine simulation engine time, we
Yep.
need and so the other idea here is we want to build a workable POC. So what is how flawed is this concept, which is just a systems
Well,
engineering.
it's not flaws; they're design challenges.
Right. And can we do sort of tweaks to it to make it work, or is it just a complete rip and replace? Like I guess Boyd's discussion on 40 psi and putting the pressure inside,
Well, now you have the
pretty much
opposite problem that you're going to be pushing the PCB up toward the copper piece,
right.
and if you had the copper piece at that thickness, I assume that's like an inch thick or something like that, would give you a fair amount of mechanical strength. And if you had a lot of contact surface between the copper piece and the top side of the printed circuit board for mechanical strength, then that would reinforce the printed circuit board.
Right. Now the challenge there is, like he said, he needs a bars with lots of he needs to at least double the screws here, you're thinking. And you need the bars down through the middle here. That causes a whole raft of routability problems in the PCB, right?
Yeah.
So yeah, so I guess one of the core premises here is that we can do this with this sort of rim all around the outside and on the back side.
Yeah. If the top side of the printed circuit board had enough keepouts on it so that you could have a lot of the ribs of the copper piece there touching the top side of the printed circuit board, not for cooling but for mechanical strength, then and you could get enough screws around the rim of this to seal it. And then the only thing you'd probably have to do, like Peter said, is put ribs on the bottom cover there so that it doesn't bend enough to disturb the seal that you've got around the rim.
Actually, just on that one, there is a possibility, whilst we couldn't I don't want to put extra screws through the PCB, we could put so it depends what you mean by ribs, but we could actually build up the lid all the way to actually land on the PCB here. Like here and here, we could do a bar all the way across.
But it's the wrong, well, it depends on whether you're doing vacuum or pressure.
Yeah, I'm talking about vacuum. So if we did it between those two, then that would sort of support the middle a little bit.
Right, because the PCB is going to be bending towards us if it's less than atmospheric pressure for the coolant that's in there.
Yes.
So if you had
but if we do that, the water's not going to flow. We're going to block the immersion.
You could probably get away with some round or rectangular or something like that pads for the bottom cover that would go up and touch keep out areas on the printed circuit board.
Okay, well that would work.
Can I ask a basic question? Is the water present pushing against the PC board only from the bottom?
Yes.
Say that again. The water.
I wanted to know if there's any water above the printed circuit board.
No. So it's dry. So the idea is this side. This is the uniqueness of the design. It's like this side is the immersed side, and this side is conductively cooled. So the water is contained in this manifold.
Yes.
So the water comes in through this blind mate interconnect, this Stolbley here, which might change for OCP Open Standard 1. The water comes in. It basically flows down through all of these ribs within the manifold to conductively cool these plugged-in modules, and then it comes out here, and then it comes down here to the lid, which then you can see just there. It comes out and floods into the immersion chamber area. So it covers all these components, comes all the way across, and then comes back out here. Again, this is, hang on a minute. This is, so it comes in here and then comes back up and returns back into the manifold through here. So there'll be a rubber gasket connecting these, which again, pulling the vacuum will make these mate even tighter, which is nice. And then it will be ejected out here back into the loop. So this is a loop that will be in the wall. Now, the only other piece that we had potentially on this is we did want to control the flow. Now, I'm not just think one phase a minute, because two phases may complicate this, but we wanted to maybe have some flow control inside here, like a little motorized valve opening up and shutting the amount of flow going around here, because we wanted the ejected water to always be maintained at one temperature, ideally 65°C, so that we can do energy reuse without having to do any additional heat pumping. So you can, I guess 65°C is a critical temperature for energy reuse, like heating buildings, etc. And I think it also kills E. coli and stuff like that. So 65°C is a magic number, which I think some of the silicon guys don't like. So then, it's a case of what's the differential? I think what's the differential with a conformally coated and copper coated chips here? What would be the junction temperature, the water temperature that we'd actually get to? And if that was as close to 0 as possible, then 65°C would be fantastic temperature to hold those dies at. In fact, that's what IBM run their System Z machine on. They won't let it go above 65, whereas most commercial devices are 85°C, or they've even pushed up to 105°C these days.
But the really critical thing is the junction temperature in the device. And so if you have the water at 65 and you have a very thin conformal coating, it's easy to predict that the junction temperature would not exceed, for example, 90°C.
Yes, and that's my hope. And if we can stay in the 80, I mean, 85 would be a magic number because that's been used forever. Like I say, people have pushed it up to 105 these days because they want that extra margin. But yeah, if we could keep it to 85 and we could eject water at 65, we have a massive benefit for energy reuse. I mean, typically it's more effective in colder climates where you need to heat buildings, but heating water or other uses or farm, they use it for in industrial agriculture, like big greenhouses and stuff like that, warming those up. Or swimming pools, etc., etc. So the energy reuse means that basically your computer's running for free, or you don't have to pay for gas heaters or whatever to heat homes or swimming pools, etc. So you get a double use of the electric used effectively. So that's another key part of this design, is we're designing with energy reuse in mind at the beginning. So because we don't know whether this processor is going to be burning a kilowatt or 200 watts, and depending on the load of the processor, it's going to vary. We want to control the speed of flow through these modules so that the outlet is always 65°C out of every module. So I don't know how that's going to affect the two-phase. That's another dynamic that might affect the two-phase operation. I don't know. And that's where, again, I don't have any experience.
So, Alan, I think the current state of the art is around 1 kilowatt per centimeter squared. And we would need to do better than that in order to excite people.
And do you think that's possible, or do you think
I think it's likely, yes.
Okay. And by the way, if we can put the words in this proposal and we can make statements like that, this is a little bit new and radical. Nobody's doing it like this. But if we did do it like this, it's still a bit of an unknown. There's a lot of if, buts, and maybes. But that's the whole idea of the DOE funding this. If this works, it would be tremendously. I mean, this is extremely cost effective. From a systems perspective, it just solves so many problems across all the silos that we can't solve today because we all live in our silos and we won't change things around it.
So
And
Alan, can I ask you a question about timing? And the reason I'm asking is that I plan to be testing these features of the conformal coating over the next month.
Oh,
so
wow.
3 or 4 months from now, I'm going to be able to tell you whether it's 2 kilowatts per centimeter squared or the delta T between the water and the junction temperature is 15 degrees. I can give you numbers for that, but I don't know what your timing is.
So the timing that we've got is basically governed by the government in this DOE Oak Ridge National Labs New Frontiers RFP. They're saying that they are it's with procurement at the moment in terms of releasing the final RFP. We've got the draft one that I think I've shared with you all. If you don't have access, let me know and I can point you to it again. It's on the wiki actually. I believe it's on the wiki. So the RFP's there. So once they do the final release, they've said they will want responses in 4 to 6 weeks. And the responses can be no more than 50 pages, which is a lot. And so I was going to try and get everything. This is one section of the proposal that we need written. So what I need companies that would enjoy the money being funded to do this work, this research. From an OCP perspective, we want to end up with an open standard here. So these pieces need to be pluggable in some way, like an IBM PC. So it's not that everything that's proprietary can't stay proprietary. It's allowing people to innovate between the interfaces is a critical thing. We just want to have the interfaces here so that we can construct this.
So what month does the proposal need to be final?
Well, so basically, I've not seen the final RFP yet, and the clock starts when they drop that final RFP, and it's 4 to 6 weeks. So if it came through today, we'd have till the end of February or middle of March to get the proposal put together and sent to them.
I see.
So, to be honest, Peter, I mean, the fact that you're making progress is great. So depending on where you're at, it can contribute to the quality of the proposal by stating facts. But equally, if you haven't got there, it can be in the proposal that this is what we're doing. This is the wet finger, what we think we'll be able to achieve. The whole point of the funding is that we can actually test it out in this format and see if it's achievable.
Yes.
So I don't think it matters. I mean, obviously, if you've already made the progress and you're contributing that, then it's a cast iron fact. But we're trying to put it into this format.
So mechanically, this would be a whole lot easier to deal with if this was conduction cooled on the bottom instead of immersion cooled.
But you wouldn't achieve the performance you're looking for.
Yeah, no, I think the simplicity of this is the immersion, to be honest with you. This will be one lid. So the other thing is carbon embodiment. So this design is all about sustainability and, the carbon neutrality. And so if we could work with this lid, with one lid and one manifold, every time somebody else designs a chip, they're just using the same. If they decide that a chip is old and they want to upgrade it, they can upgrade it and use the old manifold and lid. So the longevity of the embodied carbon could be decades rather than 3 to 5 years as a data center is today.
So the idea is that you would disassemble this, peel the printed circuit board off,
right?
Replace the printed circuit board with the new tech, put new gaskets in, and bolt it all back together.
Exactly, and this is a very modular system. This is one module. So if you take Frontier as a supercomputer, that would need 50,000 of these modules. Now, another complaint the government has is when they move from Summit to Frontier, eventually they'll just bin all of Summit and replace it with Frontier, but they would like to be able to upgrade pieces of it. And so you want that modularity, plus you want that composability, so that one module could be a GPU, another FPGA, another CPU, or a switch, and you want to mix and match those for your application needs. And you want bandwidths, you want the wiring between those processors to be very easily and effectively reconfigured for your application, rather than going up and down through spine leaf networks or whatever, and maybe not being enough, and burning a lot more power compared to a big fat pipe between two processors sat next to each other.
Now, what do these 4 screws on the bottom cover actually go to?
Yeah, sorry. This is so the ejection of them is just they're all in the model. They're all just in the same box. So that they basically bolt these all 3 of these together is a fundamental thing, and then these little ones here also do that. But the thing here is it gives you these guidance legs, and so if I reassemble this. Let me just, there you go. So reassembled, you see we've got 2 power pins here. So this is the 48 volts that comes in through the wall as well. So this is a very efficient interconnect.
So what is this whole assembly actually touching when it gets bolted together?
So basically, this is the module, and it goes into a wall. So if I put the wall piece in, this is the mated wall that it would mount to. So as you, let me just, so basically you wouldn't move the wall, you would move the module, but you can see those 4 guide pins align you to the wall before the mating of the power and the water.
And the highlighted part now is made out of what?
And that is the wall itself. So see, this is where I need to maybe, let me just open up. This little animation will give you. So if I just play this a moment, it just shows you that that's the media being ejected. So that's all the interconnect, 320 transceivers on this setup at the moment. These are the topology connectors that connect between modules.
There might be some room there for ribs. And room there for ribs.
Well, yeah. If we can get the water flowing
to
through.
flow around it. Yep.
So this is just showing you can have these modules can be anything, including opticals and switch modules, as well as a bunch of accelerators or even new tech from a startup. The idea is startups can begin to compete with the likes of NVIDIA. So now we put this module back together. This is the bit I wanted to show you. And we plug it into the wall. So there's a water inlet, obviously, there. So there's the wall. Look, it's a piece of the wall, right? And just showing you.
But is that copper, aluminum?
So, well, actually, that's up for debate as to how we put that module together. I was thinking that this could be also a little bit of a brick approach, but the idea here to show it is that is the wall. Basically, you will build your data center. There will be no 19-inch racks.
Yeah.
Just like in your house, you have water and power in your house. We have water and power in our walls here. So effectively, if I can, my mouse doesn't work here. Let me just.
But you also have some mechanical strength in the wall.
Yes. Well, you'll be constructing this wall, right? So this would be a construction of the data center.
Right, but if that wall is aluminum or something like that, that's got the I assume the far side of it's going to have some kind of printed circuit board on it for power distribution. And
well, so each let me just flash up another older presentation. I had an earlier version of this. So the how we build the wall piece, I've gone through a couple of, let me just Oak Ridge National Labs. This is where I did the Frontier supercomputer when I was explaining it. So this is a Frontier machine made out of wool. Okay.
And the walls would have modules on both sides then.
Yes, so I got modules on both sides of the wall here. Yes, you'd construct the wall so that basically you can plug on both sides. Then this is the one I wanted to show you. This is, in fact, if I go into animation mode here, let's bring it up. So you can see here, so this is sort of showing separate pieces of the wall where you've got the main copper pipes running up and down each column.
And those are QDCs on there?
Quick connects, yes, yeah, quick disconnects. And you see that each column, now this is 16 modules. We've turned the modules around 90 degrees and there's 8 modules per column now. And you see a heat exchanger at the top and there's a pump at the top. Now this is all, again, this is all cartoon, so don't take. And so this is a close-up of the wall. And you see in this particular design, we had those valves. They would be variable valves. It would control the inlet so that the outlet was always 65 degrees C. So that was so we need some sort of control there. So I was thinking we design this into the wall piece or into the modules themselves. Again, I think we had it in the wall piece. And then the gray brick in the middle is the power supply that takes the 320 volt AC or the DC facility power and gives you 48 volts DC for the module. So you can see the pins plugged in on the lower module and the pins ejected on there. And so the distance between the facility power and the half a volt that goes to the chip is only a couple of inches. Whereas if you look at any bloody server today, they've got copper bus bars as thick as you like, trying to avoid the power drop. And so we've just coupled it really close. So the efficiency of the power delivery is much better.
So the PCB is going to have the 48 to whatever.
Yeah, and then the PCB has the 48 down either with two steps down to half a volt, or even people are doing it in 1 step now.
Yeah.
And we'd also have bus bars running down the 48 volt as well. So you'd have redundancy between these power supplies. So if one failed, the others could step in to power the module. So we're thinking along those lines. But yeah, so how we actually construct this in reality, we decided we might be good to do it in a little brick form, a little molded brick that you would plug together as you construct the wall. But at the moment, we haven't taken that one much further. But this is another piece. So in one column, if you're at about 1.5 kilowatts per module to 2 kilowatts per module, because you've got to cool the media, plugged in media as well, then we're in the region of 8, in the region of sort of 15 kilowatts per column. So there's a heat exchange company that I met with at one of the OCP Prague, I think it was, where it looks like a fairly small unit would do a 15 kilowatt heat exchange to the facility water.
Oh, Alan, what is the area of the printed circuit board?
The area is roughly, the PCB itself is roughly in inches. It's about 6 inches by 4, maybe 5 inches now.
So I think that you might somebody might ask for a lot more power. You got 24 square inches, and they're going to say, we need 1 kilowatt per square inch. So now we're talking 24 kilowatts.
Yeah. So, we're at the cubics as well with the media. So I guess with regards to this is, ideally, this would serve not only high performance computing or decent performance computing, should we say. It would serve the whole industry, a little bit like the PC has served the whole industry for decades. And the whole idea of this modular approach is it can work in the data center, or it can work in a telco box on the edge, or you could have a couple of modules in your home with the water piped into your hot water tank in your house HVAC system, and or any offices. So any edge implementation then Dell and HP would go away effectively, because only the component pieces would be built by the silicon manufacturers or the memory manufacturers, and then it would be all about the wall in the pieces. buying the pieces from the various vendors rather than buying the complete systems from the vendors.
I think that's a great concept, but I'm just saying that the data center people might be asking for more power.
Yeah, well, so what I hear, Andy Beckelsstein basically said he felt that a chip, you know, with all these chiplets in it, that he felt they could get 3.5 kilowatts for cooling that. Now, when they all talk about that so you are right in terms of they talk about the thermal cooling is the area of the silicon. But to be honest, to get the power around it, they all build bigger modules with the power supplies to actually deliver. So the quote of a kilowatt per inch squared or whatever is really at the silicon level, and they don't account for the power supply infrastructure around it they need anyway. Because if you look at an NVIDIA module, the module is about the same size. This is a little bit bigger than NVIDIA's module.
Okay.
And they're at 700 watts with the H100 now, and I guess there's forecasts of going to 3.5 kilowatts. Well, that was Andy Beckelsstein from Arista Networks, the founder of Sun Microsystems. He basically reckoned in the law of physics, we can get to 3.5 kilowatts in one of these 100 millimeter package sizes with chiplets in it. Now, look, so by the way, I mean, if in this module we could cool a 3.5 kilowatt chip with this two-phase water approach with conformal coating, I think it'll be a home run. But I think if we can only do a kilowatt, we will serve 80 to 90% of use cases. And maybe like with your architecture, Peter, which obviously Michael and Jason don't know, but with your architecture, Peter, you take it to the next level. So maybe that's where your architecture takes over. When we want to go to crazy supercompute density, then okay, you go back to speciality world. But this is sort of covering 80% of use cases is the idea.
Okay.
Yeah, Adam, I think your power is from the bottom side get in, right? But the bottom side, that's the immersion area, right? And I most concern is about the leakage. Although you put the pressure inside, you vacuum inside, but if they still have you cannot completely seal that. The inside pressure will gradually to get higher and higher. Eventually, they will get leakage. If you have more kind of connection area, then that's the issue. Is that possible? You can put the power from the top side in through the PCB go to the bottom side. Then that's you only have the small tank, the sealing. You just need to solve that issue, right? You don't have right?
Sorry, you're talking about this power in?
Yeah. Because that need to go through the tank, right? That you need to create the opening and with some sealing material.
Oh, I see what you mean. Let me go back to the model to show you exactly how we.
I just jumped in, so that's why I try to get the.
Yeah. No. I think that's okay, but I may be wrong if I'm not hearing you correctly. So let me just so if we just remove the wall a minute. So here,
yeah.
So here is the power pins coming through, right?
Yes. Yeah.
And so if you look, if I just eject this out again. So if you look, the actual frame here goes around the power pins. So there'll be this is the sealant around those power pins. So they so they would be effectively sealed away from that, bringing the power into the board.
Okay, that's isolated from that area. Okay.
Yes.
Yeah. The second thing is I think Michael already mentioned the reinforcement layer, because we are not working this kind of that, but we do lots of the very big the socket, CPU socket, maybe ASIC socket. That's about 8,000 pin count to the 10,000 pin count. Okay. And
Yes.
we see that issue with the PCB warpage issue due to
Yes.
the reinforce.
Yeah. Good
And
point.
here is because we usually use a backplate to support that. But there are some capacitor area they occupy the area. We cannot put the whole piece of the backplate. We need to cut out something. And that case is typically tough and to create a uniform pressure. But for your case, you just need the whole edge area to create a uniform force to make sure that the sealing without any leakage, whatever inside or outside. Okay. And I have no idea if with this kind of you will add some gasket, some sealing material, but how about the long term? And you can make sure this kind of any kind of the leakage. If the board itself there's some a little deformation at the edge area, that's
Yeah, the deformation of the board will likely pop the solder balls on the big package. That's from what you were saying. I guess that's a possibility. That could be an issue that the pressure causes a deformation of the board.
Yeah. So I think Boyd last week was talking 28 pounds for the coolant pressure on a single phase.
Yeah, they were talking about a 40 psi, but they said they
40.
need
Oh,
40 psi they designed for, but they need to be able to sustain 30, so that the 40 is a margin.
Yeah.
you know, that's almost 700 pounds of pressure on the printed circuit board.
Yes,
Oh,
right.
That's very high force. Okay. So it still need to get, as Michael suggests, need to run some simulation.
Well, this is where if put in the vacuum is a lot less pressure. If you're down in the 8, I mean, it's still not small. But...
Peter, was that 40% of an atmosphere or 60% of an atmosphere you were suggesting for the two-phase?
40%. Yeah. I have a I plotted the pressure versus so let's see, at 40% the boiling point is let's see here.
Yeah, so it's only 140 pounds of pressure at 40%.
At 0.4 atmospheres, the boiling point is around 75 degrees C.
75 at 40%, did you say? So it'd be even higher then.
And at 0.2 of an atmosphere, the boiling point is 60 degrees C.
Okay, so we're probably in the 0.3 range or 0.25 range then. Peak.
Well, so what will determine this is the delta T between the junction and the water.
Absolutely, absolutely.
And I think you're going to see something around 15 degrees C for that. But I don't have the data yet. But that's what I think will happen.
So if we were at 15, then we could handle a boiling point of 70 to hold 85.
That's right.
And by the way, so if the device was only burning much less power, it wouldn't boil, but then so would that become a problem?
No, so that's why you have the AI. So if you're not boiling, you're in the single phase mode, and you optimize for that. And then there might be just some components that are really hot, and then they boil.
So the AI would control the valves then, I guess.
That's right.
Maybe.
That's right. Yes.
Okay, nice. All right. Well, so okay, so oh, by the way, the other part of this on the electrical front is if you notice the substrate, if I just hide this a minute. Oh. There we go. The substrate is getting so big on these chips. Why not cut out the middleman from a signal integrity and power integrity and actually make the whole module the substrate. And I've spoken to a number of substrate manufacturers, and they don't seem to think it's impossible. I mean, it might not be necessarily that cheap, but it's not impossible. And I think that would then, in terms of warpage of balls, because on these huge packages, you get any warpage in the PCB, as Jason mentioned, and you get cracks in the balls, and then you're screwed. That would take that away if we actually could drop these chiplets down into down straight onto the module itself. Then that might reduce the area where single components of stresses as the board does warp a little, and might give it a more survivability. But I wanted to do that as a separate exercise because obviously everybody will supply you with a packaged chip today. So we want to work with these big packaged chips. So, but in the future, hopefully we could say, let's get rid of these packages and make the module the substrate.
Yeah, I think that's a great idea, but I want to ask you, what are these components on the outside of that white square? Are they
all the gray ones are basically the power. So these are industry standard that NVIDIA drove. Every power supply manufacturer makes this format now. So these are 170 amp dual phase power little bricks. They can deliver down to less than half a volt. And then these big ones on the end here are 48 volts down to 12. So these modules are 12 down to the half. So it's two stage. So, I've got 2, 4, 6, 8, 2, 4, 6, 8. I mean, basically, this could deliver 1500 amps plus. I've just sort of did a space model so we should be able to power just about any, a kilowatt or more of this device and the modules on the back.
And are those cubes the actual size of the actual
Yes,
component?
they are high profile. So they're about 8 millimeters high, I think, 7.65.
Okay.
So the lid, we need water to flow across the top of these and around them. And so that in terms of the blocking of the water flow, that is obviously a concern as well. So we need to do the CFD on the flow of water around everything here in the turbulence.
Okay.
Now, could you design the QDCs for the water and the pins for the 48 volts so that they would have, say a half an inch of engagement? Really, really deep engagement. If you did something like that, then the distance from your wall to this printed circuit board could vary by half an inch or something like that. So
yeah, well, so let me put the wall up. Do you mean so
right.
this is
right.
like
so your QDCs have like a minimum and maximum engagement depth.
Yeah, I'm not sure what that is.
If that was relatively deep, then the cover plate that's going to go between the wall and the printed circuit board could vary in dimension by a lot.
Oh, yeah. Oh, absolutely. Let me put the lid back on. Oh, and now I've got it down. Hang on. Let me just. There we go. So that's the setup right now. So even with the current setup I've got,
you've got plenty of gap in there.
You've got a big gap, so we could lift this lid quite considerably, yeah.
Yeah. So the other thing I was thinking is using the wall for mechanical strength for the immersion cooling cover.
Okay. So obviously these modules need to be sort of blind mateable, and
right. But right now you've got
another screw in here that would screw this to the wall.
Well, right now you've got a big gap between the wall and the cooling cover.
Right.
Why?
No reason at all, really.
So the ribs, if you put ribs for mechanical strength.
Well, no, having said that, I guess it's literally the Stolbley connectors here. I'm not sure if these are fully mated home actually. This might So this is probably not fully mated home. I think it's fully mated if we pull this down to
But in
here.
any case, you're still going to end up with a gap. So if the unmated distance there is about the same thickness as the cover,
Yeah, so
you've got
actually
about
that's 6 millimeters. So if
Yeah.
I do -6,
you're still going to end up with like a 12 millimeter gap between
so the gap there is 12, spot on, 12.8.
So why not have ribs on the
Outside.
yeah, on the back side of the cooling cover.
Yeah.
So
Okay.
it can derive mechanical strength from the wall.
Yeah, like I said, I think I said earlier that this can be thicker for sure. So whatever we want to do to this lid,
Right. So if you're running a kilowatt, that lid might be 12 millimeters thick instead of 6 or something like that. To allow more coolant flow through there.
Yes, if that makes sense. Now,
But
obviously, we do have the coolant flow is somewhat limited by the area of these the Staublies we've got selected here are 25 millimeters squared, I think.
Right.
Is the area of that is going to be the main limiter of water flow depending on the pressure.
Right, but you don't really know what the components on the printed circuit board are going to look like 5 years from now. And if this has got that kind of a life.
Well, one would hope they only get smaller, but then the power demand gets higher typically as well.
So I mean, you could have little bitty heat sinks on the top of them or anything like that, off into the coolant flow, and you've got
absolutely.
So you've got 12 millimeters in there to play with. So if sometime in the future you could expand that cooling cover there from, you said what, 6 millimeters now or something like that, to like 18 or something, whatever was necessary to handle future technologies that are in there.
Yeah, that would work.
And then if the top of the cooling cover actually pressed against the wall, then you could put, like, for a 6 millimeter one, you'd have 12 millimeter ribs or something like that on it to give you mechanical strength for the cover, plus extra mechanical strength from it sitting right against the wall. Now, I assume you're going to have something on the wall to stop this module from flapping in the breeze when you tighten those screws.
Yeah. So the wall, again, I haven't finished. We haven't done much on the wall versus beyond a sort of a block concept like this. But so these screws here would actually, they not only do they screw the module together, they'd have a hole through the middle here, and you'd have a screw on top of these that would mount. So the length of these pins would basically make the module hang on the wall nice and stably. The wall would need to be obviously strong. Each of these modules are going to probably be 1 kilogram to 2 kilograms in weight.
But is there a spacer or something like that between the top cover and the wall that's part of the screw, or?
Between the top cover and the here.
The way, yeah. And that what stops me right now from taking the module on the opposite side of the QDCs and pushing it closer to the wall?
Well, obviously you've got the Staubli interconnect here is one. I was assuming you'd have some landing pieces here where the module would actually hard land.
Okay.
And then these would be just light screws to hold it in place to stop it vibrating out as much as anything. I didn't think we needed anything significant other than just holding it in place, because the length of these pins would mean this hangs quite nicely, would be the idea. And again, I'm not a mechanical guy, so take it.
Well, I mean, some of the numbers are easy to derive. So that if you've got a 24 square inch surface area for the PCB that's on there, and you've got 40 PSI, just multiply the two, and that's going to give you the pounds of force on that top cover. And it's almost 1,000 pounds.
Right, wow.
So doing the two-phase cuts that by 75%.
Right.
So mechanically, the two-phase would be much, much easier to deal with than the high pressure that you'd have for a single phase.
From the Boyd,
Yeah.
and the Boyd suggest. Yeah. No, I mean, so to be honest, my discussions with Peter and Anand at UIUC were really made me come back to this design. The beauty of this design is its simplicity in a lot of ways with the lid design. You don't have to keep doing different design lids to mate with the different chips. You have one lid, the water does the mating. And so that's what I like about this little mini immersion.
So there's nothing that would stop you from, if you had a low power PCB in there, from doing a conduction cooled instead of
exactly. If you've got a little 200-watt chip, you just stay in single phase. And it's water. The other thing is it's water, so it's a lot more every time I talk to people about oil or these tricks, everyone, the industry says, oh, we've solved it, we've got a clean one, a bit like vaping versus smoking.
But it also takes a lot of horsepower to move it around because it's viscosity of
in terms of the thermal transfer. And this is what John Summers told me from Rise Institute. So it just feels as though we're just saying sustainable from the get-go here across every dimension. And that's what's so nice about this. And it feels, actually, the more we talk about this, so thank you guys, I'm very engaged in discussion. I just feel that this, if we can write it well and show the potential, it will show the DOE, this is a thread worth pulling, right? And
yeah, well, I think a lot of your proposal has to be the what ifs on here, so that you could do conduction cooled on both sides of the PCB with, like you said, a 200-watt board, or immersion cooled. You could go very, very high, and the mechanical design is adaptable to different sizes of immersion cooling chambers. So that leaves you plenty of room in the future for future tech, for whatever the chips are going to look like.
Conduction cooled, where you'd actually still design the lid to mate with the chip, or gap pad.
Well, the top cover there would have coolant passages in it, just like the copper one does.
Yes.
So there wouldn't be, in that case, you wouldn't have any liquid actually touching the PCB.
Right, but you'd still have a thermal gap pad of some sort.
Yeah, you'd have a gap pad on both sides of it. And, so for a low power one, that would probably be easier to design.
I guess than doing the conformal coating of the board.
Right, because now you've just got normal PCBs on there.
Then you need a separate lid designed for each module. That would be the only issue there.
Yeah, I don't see that. Yeah, but and like Peter said, if that wouldn't handle, a kilowatt, so you'd have to do immersion cooling for something of that magnitude. But there's enough gap between the module and the wall, so that you've got plenty of room in there for whatever design
for a conduction design. You're right. Agree.
Conduction design, immersion design, giant immersion design.
To be honest, that was hopefully where we were going to go. That you could do the Boyd solution, except for the Boyd solution needs this massive pressure support, which for me made it a little bit. It made the whole idea untenable.
Now, what about the network connections between this module and the rest of the world?
So basically you can see this is full of media. Okay. These could be cables instead. If you've got an IO heavy device, you can actually replace these with cables.
So nothing through the wall itself. The wall is just power and cooling.
The wall is just power and cooling, correct.
Okay.
And then these 8 connectors on the side here, we call these topology interconnects. So I'm working with the interconnect group on this aspect. And
so you build a hypercube or something like that using the ones that are out on the edge.
Exactly. Right? We could so in fact, if I go back to that presentation.
So then some of these modules need to be switches.
Exactly. Right. So you're on the button. I love it. Just a minute, let me come back. So I need you to watch one of these other presentations, because you'll get the big, if you watch my OCP Summit presentation, you'll get the big picture. Okay. So remember we came to this. Let me replay this. So you've got the module, you've got the wall, and you blind mate populate the wall like a Lego brick until you filled it up with your configuration. And again, if it's a telecom box, it might be a small wall on the side of the road. You know, the telecom engineer opens up and he sees these modules. If we wanted to do the Frontier supercomputer, if you know the configuration, that's an AMD CPU and 4 GPUs. So we would make that up, and in a node is or 2 nodes in a 1U box, I think they have. So we could replicate that with 10 modules, and we can wire it exactly as they've got that wired, so we can run their software stack. We could do the Grace Hopper. If you know, Grace Hopper is a massive band of 7 PCI links between the two. Well, we could those E3 modules, we could get rid of the modules and just cable between 2 modules, and we have the bandwidth of Grace Hopper with 2 modules. Okay, it's not quite as dense as Grace Hopper, maybe a little bit more power on the I/O, but it's there.
Now, if you also did a good job on the construction of the back wall, there is nothing that would stop you from having a double or a quad module.
No, exactly. There is that possibility. So you could actually build a Grace Hopper and take up 2 module sites. Absolutely.
Yep.
Yes. Very good point.
That needs to go in the proposal.
Yes, yes. Summit node, there you've got it was 1 CPU, IBM Power 9 and 3 GPUs, NVIDIA Volta. And then we just covered a couple of others. Oops.
A friend of mine works in the power group.
A GPT-3 optimized AI cluster, maybe an FPGA pooling. You can have optical. You can have some optical switch modules, circuit switch modules. And I've been talking to a bunch of optical switch companies, so it looks like they might be small enough that we could put the optics into the switch. We are looking at co-packaged optics, so you need to come to the interconnect work group to see what we're doing on a universal interconnect that gives you electrical, optical, near packaged, co-packaged active cables. And then you can have a Burger King compose it your way. And in this one, you can see the switch in the middle. So you don't have to have a switch at the top of the rack or the middle of the rack. We can put switches wherever we want them. Or we can hardwire everything and not have any switches.
And if you do a hypercube, you don't need a switch.
Exactly. All right. And then this is a water piece that we've already discussed. So this is the sustainability. If you know sustainability, it comes in 3 scopes. So this is a reduce operational emissions. So this is we feed cold water in and we get 65 degrees C out because every module ejects only 65 C. In scope 2, from the discussion we said, you're building a domain-specific architecture. So if I need a Grace Hopper fat pipe, I can do that directly. I don't have to go up and down the switches and switch network and burn a shit ton of power. We've got less data movement. These modules are inches apart. We don't have to go in and out through 18 inches to get out of the 19-inch rack and back into the 9-inch rack. When if you look at 2 1U boxes, chips, they're only an inch apart, the chips are, but we have to go through 3 feet of signal integrity loss. And picojoules per bit to get over that to actually connect, when in reality they're only a couple of inches apart. So our 19-inch rack is now a module, a 3D module. More efficient power delivery, as I explained, and then the indirect emissions, we're using less raw materials for the same machine, and they're very reusable. So that was that. And then we talk about little benchtop environment, etc., of putting these together. Anyway. Don't want to drift off there, but does that make sense?
Yep, an awful lot of sense. So architecturally, this is fine. Electrically, this is fine. Cooling, I think you're fine. Mechanically, you've got some challenges.
Right. Okay. Well, that's what we're. I mean, it's a case of how big are those challenges? Is it fundamentally flawed, or?
Well, that's why the gentleman from Boyd last week was talking about putting more screws in the cover and having screws in the middle of the cover, because that gives you a lot of mechanical strength to handle the 1,000 pounds of force on the cover.
Right. That's if we take his design approach versus this pulling a vacuum approach with the immersion and the board. So are we still what mechanical challenge if we took this immersion vacuum approach, lowering the boiling point of water?
Well, I don't think there's any problem with the Boyd approach either. It's just going to require a lot more metal
Yeah, and I think that the more holes we put through the board, the more challenging we are of getting all the signals cleanly between the connector and the chips, right?
Yep.
So that, I mean, that's why we've got it on the outside. So I mean, I guess my question is, mechanically, are we within the realms of possibility with this conformal coating in vacuum approach with water?
Yeah, you're only at 247 pounds of force on the cover with the vacuum approach.
Are you saying that with a smile on your face?
No, well, I mean, it's a quarter of what it would be with the single phase coolant.
But it's still a challenge, I guess.
It's still a lot.
Right.
And that's why cold plate works nicely, because none of the mechanical stress goes on the components.
Right. Yes.
But cold plate has its limits.
Well, so I guess, well, first of all, I mean, you say you like everything else, but you think the mechanical challenges. The question is, within the framework of this design, do you think the mechanical challenges are completely broken or
no?
workable?
I think they're all solvable. And the gentleman from Boyd was suggesting additional screws in the middle of the cover, and I think that would be a good idea. And
I think that's going to be a challenge. I mean, we might be able to put extra pillars, so when we pull a vacuum, the pillars take the strain. Yeah. I'm not sure I can put additional holes through the board and between the. Or that
something to study. Something to study. And the same thing with the ribs on the copper piece on the top there, having more of the ribs actually, well, in the vacuum side.
I think that is perfectly plausible. I think that makes a lot of sense.
But you really only need that on the pressure one. The low atmospheric one is going to pull the printed circuit board away from the copper.
Right.
So then, in that case, the
lid needs to be more stronger, and you need some pillars from the lid that push against the PCB to stop it from collapsing.
Right.
So I think that's doable. I can see us being able to do that as long as we don't impede the water flow too much. Yep. We can put a couple of pillars along the side of the chip. I mean, that's where it feels. I mean, based on what you're saying, if we go with the vacuum and water and conformally coated approach, it's a bit more pushing the bounds of what's been done, but Peter's been working on that anyway, and so is Nanad and UIUC. So it's pulling the thread on that approach, and it looks like the mechanical challenges are more solvable than the supporting 40 psi with a pressure being pushed outwards, exploding everything apart.
Yeah, but that's probably still solvable too. You know, you've got plenty of room between the wall and the cover to make a cover that's 12 millimeters thick or something like that, with lots of ribbing on it to support the pressure.
Yeah, I think it's a stiffening on the back with because Boyd wanted they wanted the 2 loops of water, one for the chip and one for the rest. So
but you've got plenty of room in there to do anything you want on there and make it give it sufficient mechanical strength.
Okay.
And if you had more of the copper ribs touching the printed circuit board to stop the printed circuit board from bowing toward the copper, then that might give you sufficient mechanical strength there too.
Right. I guess what we need to do here, in my mind, we're changing, so you can see this is this concept. The problem with this concept, and we've had discussions at the main group level, is that this is so radical. You know, like you're getting rid of the 19-inch rack. People just can't get their head around how would we even start doing this? We'd have to rebuild our data centers and from the ground up, right? So
well, we're a 19-inch rack manufacturer, so I'm not so happy about this either.
Okay, well, you could be the infrastructure manufacturer. Yeah, well, and there is that side of it, right? I mean, that's the other thing. The incumbents like to keep the gravy train rolling, and they just make tweaks that keep their main gravy train rolling. So, whereas we're trying to start with a clean sheet. So, I mean, it's got many challenges, but from a business and a technical perspective, and like if like in the EV world, you're either, as I've said before, if you're on the call, if you're a Tesla and you got, or Elon Musk and you got a couple of $1 billion in your back pocket, you can do it yourself and sod everybody else. But the only other way of doing it is in a community like OCP, is my belief. If that's possible, but it would be good for the wider community. Yeah, so I guess I'd like to get to a POC where we can put all of this together. So we can't boil the ocean on any one of these. I think we need to take one approach and say, well, we can prove it here, and maybe we can put some hooks in so that we could the design has the potential to support other approaches like Boyd's or conductively cooling, etc. But we take one approach that says, well, we think this will at least get us to 500 watts and hopefully get us beyond the kilowatt. And at least it gets us to a POC design.
Now, is there any benefit to running something other than water for a two-phase cooling? Or is the whole idea water is less expensive and more ecological and stuff?
Yeah. I think the environmental factors are huge with going to water, and I keep being told that dielectric is tremendously inefficient in terms of heat transfer compared to water.
And expensive.
That's right.
So if we're going to do this immersion, we need to go to water, really. We need to take every advantage we can if this is going to work, I guess.
Yeah. The coolant that Cray was using was $600 a gallon.
Oh, wow, shit. Mind you, water's getting up there if you buy it by the bottle at the airport.
That's true.
There could be some applications that combine water with ethylene glycol for cold temperature.
Yeah, well, 25% or 50% is fairly common in data centers too. So.
Yeah.
All right, guys, we've gone well over the hour here. Appreciate you taking your time. Fantastic discussion. Truly appreciate the input. I guess so. Just cutting to the chase is we need to. It looks like both Michael, Peter, and Jason, you're all contributing here nicely. Would you be, I guess, your company's perspective, I guess specifically with you, Michael, and maybe Jason, is do you think now you understand a bit more about this? Is this something you'd be like to you could justify getting involved with, or like you say, because you build 19-inch racks or whatever, this doesn't play to your desires?
Well, we also do a lot of liquid cooling equipment too, but this is so far away from any of our existing products. Our company is obviously interested in future technology, but I don't know if they would fund me to really participate in, have the company participate in the project.
Right.
I get paid to do standards, so me being on the call is no problem.
Right. Yeah. I guess. Well, it's what can you do in terms of contribution to the papers, but yeah.
Fastcom, we are currently we focus on more in connector cable and some kind of the thermal solution, but the thermal solution is currently we work on the kind of TIM material, work with the University of Illinois too. Okay.
Oh, you are working with them already, are you?
Yeah, that's a TIM material right now, and because we have the cage and transceiver, that's a service the TIM material. Okay. That's an area we are not in this kind of the solution, the product for this solution, but we just we can provide some kind of experience how to create some kind of the mechanical support for this the vacuum area. because
And you think
currently,
you get the support to, would you be interested in participating in the proposal? And I mean, the idea here is the people that put the effort into the proposal are, assuming
yeah,
they backing.
we can provide some kind of the suggestion, because from our circuit, because the circuit is big and high force cause the PCB deformation. Yeah, that's the area, but we don't have the product can provide here, but just from our design experience.
Yeah, I guess it's if we get funding, it's a case of we need to bring engineering effort to make this into a POC, right? And then to build the actual unit. So it's people can.
Yeah, well, this way, for definitely yesterday meeting for the interconnect area, that's our product, then we can support. Here, I can bring your concept to our circuit designer because they deny the backplate support, how to maintain the PCB deformation. That's we just provide this suggestion experience for you. And definitely, we, as the Michael mentioned, that need some simulation work to calculate. To prevent. Yeah, that we can support this area, but not the product. We just experience. Yeah.
Okay. And
Okay.
Peter, I guess you're the just yourself, is it? Or have you got a big team behind you, or?
Oh, it's mainly me.
Right. So how do you feel about carrying on? I mean, you've already put some words in the proposal, so thank you very much. So
Yeah, this way, I think now I get more idea about this area, and I can bring back to our internal team, and we see which area we can work together. Okay.
actually, Jason, just on the thermal between the interconnect we were discussing yesterday and the chassis, the manifold, how do we make that and simulate the thermal bridge on the conductor? We didn't get to discuss that, but that's where if you do both sides of that, you might be unique to help us out on the connector and the thermal piece of that.
Yeah, that's together. Yes, because currently internally we do some kind of simulation for the cage, the transceiver cage area.
Right. Okay.
Yeah, that area. So
well,
I will bring.
That would be good.
Yeah, I can bring to our team and we can discuss about that.
Okay, so if you guys, I can give you guys access to the document as well. Everyone's got view only unless they ask me, and then I let them in as an editor. So I can let you both in. Peter's already in as an editor.
Yeah.
So Peter, just from your perspective of does this further what you want to do as well? That if we can get funding, it helps you out, or?
Yes, I'm very interested. I am limited in funding. I stretch my budget to do what I need to do, and so that's a factor. I'm also generally interested because the technology I think is very interesting, and also as we discussed, I have a model that's for even higher power, and so I learned from this, and it applies to that.
Yeah. I guess what we get done here can help prove out certain pieces for your taking it to another level.
Yes.
Right. Okay. All right. Well. So I guess we need to get words on paper in that thermal section. There are the different aspects. We really covered the immersion piece today. Didn't get onto the other ones, but. If you guys, I don't want to really say exactly how we do this. It's if we can get pen to paper and we can get some meat on different pieces, and then we can start to shape it together as a picture comes together. I think that's a good first start. So I can give you all access, and if you have the time to put some words in there, and then we can all work together on refining it for the proposal, if that makes sense.
So what other thermal issues are you thinking other than the immersion?
Well, on the other side, we got this manifold. So we got the design and manufacture of the manifold itself. And like I was just mentioning to Jason there, we need to have some thermal interconnect between these media modules that are about 40 watts each. and the manifold, or the active cables. If we put cables in and they're active, we need a thermal mate to cool the active components in the cables. So the manifold design and the thermal transfer of that, so that we can conductively cool those modules, is a sort of a separate piece. We've obviously, the other piece is the wall itself. We've got, I've got these pipes that I've just made the pipe. There's 8 modules it feeds, so the area of the vertical pipe I've made 8 times the size of the blind mates. I'm assuming that's what you need. And then, are we going to be able to pump 15 kilowatts through there? And we got a heat exchanger exchanging it with the facility water. So the design of the wall loop would need to be in there. And then the valves, we need to put valves around each module so we can control the flow through each module, so we get 65 degrees C out, or a nominal temperature out of each module, depending on what power it's burning. We slow or accelerate the flow to get
So I think many of those issues are handled with the latest thermal modeling software, and I don't have that, but I think some of these guys do have that.
Right. Yeah. Well, so a lot of there is some of this is, how much can we do with I think the thermal interface on the conductive cooling is, if it could be quite difficult to model as a first pass, and sometimes building it might be better or more reliable a measurement than or building a little test sample.
Yeah, that's needed some correlation, from simulation and
correlation, right.
Yeah.
But yeah, obviously to get a first pass, either somebody that's an expert in this just knows through intuition, versus can we do a quick simulation that will give us at least give us a wet finger a view that we've got it about right. So yeah, it would be good to have some level of simulation, obviously.
So you mentioned the 40 watt for each the module, is that right?
Yeah. So if you take the E3.S modules, a single width one is 25 watts maximum, but a double width one, which we would propose, we'd make a double width into a single width, is 40 watts. So we could do the theory.
That's a 40. Yeah, 40 watt is good number because the current transceiver challenge is a 40 watt. So
right.
Yeah, we are working on.
Exactly. Yeah.
Okay. Yeah, that's the same. Yeah. Okay.
All right. Well, so I'll give you Michael and Jason. I'll give you access if you can get time. And Peter, like I say, if you can start to flesh out just one particular, you don't have to think about the whole lot, but if there's particular pieces that you'd like to contribute to, then feel free to put words to paper around where you want you're happy to help.
Yeah.
And then we can take it from there.
Yeah.
Okay. All right.
All right. Thanks, guys. Much appreciated.
See you later.
Bye.
Okay. Bye.